Okay, so this is the first lecture on multivariable calculus, and this is the topic we're going to spend the rest of the course on. Okay? In the beginning, this is going to be kind of stuff you already know, I hope. But then by the end, it's going to be theorems that you almost certainly didn't learn in Calc 3. And if you did learn them in Calc 3, you probably don't remember them. Okay. So we're going to start with section 6.1 of Tao's book. This is linear transformations. So today is kind of a review, not of Calc 3, but of linear algebra. We have to get in the right, well, for one thing, we have to make a bunch of definitions. Okay, are there any questions before we get started? No? Okay, in that case, let's just jump in with a definition. So we've got a mapping T, capital T, from Rn to Rm, and it's linear, or we might call it a linear transformation. F. Okay, now hopefully this is review. It has to satisfy two properties, or really just one. We can combine them into one. We'll talk about that in a second. Okay, but we need to have two vectors. So if for all vectors x and y in the domain, and all scalars we have two properties. First thing is that if you apply the transformation to x plus y, you'll get the transformation applied to x plus the transformation applied to y. And the second one, if you scale your vector x by c, and then you apply the transformation, that's the same as applying the transformation and then scaling by c. Okay. Note that we can combine these. What would we insist on? T of cx plus y would be ct of x plus t of y. Okay, the point being, if you satisfy that for all vectors x and y and all scalars c, then you satisfy both conditions A and B of the definition of a linear transformation. Okay. I hope this is all review, is it? Yeah? Okay. And it's going to be a very abbreviated review. We're going to go through at least half of linear algebra in the first half an hour here. Let's look at some examples first, though. Okay. Just to kind of get you back in the right frame of mind and to tell you kind of the conventions of what we're doing. Let's have a mapping from, let's just do R2 to R2. Okay. Now, you've got to make a choice when you're doing this stuff. Are your vectors column vectors or row vectors? Okay. And I think Tau makes the wrong choice. Tau chooses his objects, his vectors that he's going to do these linear transformations to. He chooses them to be row vectors. Okay? And this is a problem. Because if you think about matrix multiplication, if we want to say that this mapping is the same as multiplying by matrix on the left, then we can't have row vectors. We have to have column vectors. Okay? Or we have to take a transpose everywhere. Okay. So I am going to, I hope we can pull this off. We'll see. I am going to try and do column vectors, despite the fact that our book does row vectors. And, I think, for me personally, every time I do linear algebra, I have to double check what's a row vector, what's a column vector, and, we'll just have to do that as we go through this. Okay, so with that said, we would be looking at T applied to a column vector, x1, x2. Right, I'm defining the operation here. And, I'll just put in something there. This is linear, okay? Now, this is also awkward, because here we have these double parentheses. The outer parentheses are kind of going with the function. T is a function, so we always do function with parentheses. The inner parentheses are because x1, x2 is a vector, and we always do vectors in parentheses, okay? So I'm just going to say we'll often drop that. We'll often drop one set of parentheses. So we would write T of x1, x2. Okay? Okay, so that's our example. What is our proof that this is actually linear? Let's do the short version. Okay, so take x1, x2, y1, y2 to be column vectors in R2, and C to be a scalar. Then okay, we're going to drop that extra set of parentheses. What do we need to check? T of C times x plus y. C times x plus y would be cx1 plus y1 and cx2 plus y2. This is, by definition, twice the first component and then the sum of the components. Okay. And then let's check what it's supposed to equal. c times t of x1, x2 would be c times 2x1, x1 plus x2 equals that. And t of y1, y2 would be that. And there we go. So indeed, t of cx plus, didn't actually give these things names, so there we go. You'll notice here that that extra parenthesis that we were not writing showed up again, and it's kind of necessary there. Are there any questions? Okay, good stuff. Let's move on. Let's look at a couple more examples just to remind you of what we won't prove these, but what these linear maps can do. Okay, they can dilate. So let's say we've got t from R2 to R2, defined by t of x1, x2 equals, say, 3x1, 3x2. Okay, that just takes a vector, stretches it out. Okay. We could rotate. Let's look at t from R2 to R2. In fact, let's do one of these for every theta. And now let's say that this is the map defined by rotation by, say, theta radians counterclockwise. Okay. Now, hopefully, in your linear algebra class, you saw this guy, and you saw how to represent it algebraically. But we don't need to represent it algebraically to check that it's a linear transformation. We just need to check that it satisfies the condition. So does it really satisfy this? Okay, and I think you could check that with the definition I've given. You don't need the algebraic version. This is saying if you stretch x out and add y and then rotate, that's the same as rotating x, stretching it out, and then adding the rotated version of y. I mean, you can just draw a picture to convince yourself of that, right? Okay. So it's linear. We don't even have to write down the algebraic version. What else could we do? We could project. Okay, to project, now we'll need a bigger space. We'll just go from R3 to R2. And projection means we forget about one of the coordinates. Okay? We could have forgotten about x1 or x2 instead. Okay, or we could do the reverse of projection. What would that, what should we call that?
My gut said injection, but I feel like that's not right, or that doesn't make sense.
I like injection. I was going to call it inclusion, but injection works too, I think. Well, yeah. Okay, so the reverse of projection, I'm going to call it inclusion. It's not really the reverse. You can't undo projection because projection is not one-to-one. It's pretty easy to see that it's not one-to-one. So there's no reverse of it. Sorry, I shouldn't call this the reverse of it. But if we want to go from R2 to R3, what we could do is we could just put in a 0 in that missing coordinate. So we could just define it to be that. Okay. What if we filled in that missing coordinate with a 1 instead of a 0?
You'd break scaling.
We'd break scaling. We'd also break addition. So we'd break everything. So that would not be linear. Okay. It's still a mapping, it's just not a linear mapping. Okay. I guess in that case, the fancy word for it would be it's an affine linear transformation. Because we're doing a linear transformation and then we're adding something. But anyway, we don't need to concern ourselves with those right now. Anything else that a linear transformation can do? Stretch and shrink, rotate, project, inclusion, anything else?
You can do nothing.
Yeah, I mean, that's a special case of, at least.
I guess all of them. Like a special case of all of them.
I guess it is a special case of all of them. You can define projection from, say, R2 to R2 as doing nothing. Anything else it can do?
What about reflection?
Yes. We could reflect, couldn't we? Good. Okay. So then our next topic is that linear transformations are the same as matrix multiplication. Okay. So let's define a matrix. Do this way. Let's call this definition / review. We're going to have a matrix, and I want its columns to be A1 through AN. And those are going to be vectors in Rm. go get the light on again. Okay, so if these are the columns of A, then A can be expressed as a row vector of these columns. Okay. Now, let's take, this is, so A here, let's get this right. A is an M by N matrix. It has M rows and N columns. Now, if X is a vector in Rn, then one way to define the product AX would be to take the sum of the jth component of X with the jth column of A. And we would sum this from 1 to n. And we would see we have here a linear combination of a bunch of columns. Each of those columns is a vector in Rm. So we would get that. We good? Now, I always need a picture for this.
Is the dimension on X correct? Because the A's are in Rm and the X's are in Rn. Are they supposed to be the same size?
No. So let's draw the picture, okay? Here's A. It's an M by N matrix. X is in Rn. So X looks like this. And that dimension is N. Okay. And so now, this is the way I always remember the product, is I'm taking, on the left I'm taking the rows, and on the right I'm taking the columns, and I'm doing a dot product. Okay, and so what am I going to get when I do that? I'm going to get a vector that is height m. So I think we got it right. And you can double check that the dimensions worked out. Right? When you're doing matrix multiplication, and this is a special case of matrix multiplication, this is an m by n matrix times an n by 1. N by 1 matrix, the inner dimensions have to match, and then the product has the outer dimensions. So our inner dimensions match, and then the outer dimensions are the dimension of the product. Is that correct? Did I get everything right?
I think so.
Good. But you should be suspicious of this. at least for the first couple lectures, because again, I'm trying to flip things from tau, for better or worse. Now, in particular, if we think about the EJ, what are EJ? I have a 1 in the jth row. These are vectors with all zeros except for 1 in the jth row. That's your just standard basis of Rn. So I'll write that. Then, if you did, if you multiplied A times the basis vector EJ, what would you get?
You get like the jth column of the A matrix?
Yeah, you'd get the jth column, so that would just be AJ. So we might even want to think about this the other way around. I mean, I don't have to do this. It's an equality. You can read it whichever way you want, but what I'm saying is you can think about this as how you define the AJ, right? The jth column is the action of the matrix on EJ. Okay. Before we go on, I just wanted to point out that we're not using any kind of decoration on our vectors. I don't know what's standard in linear algebra these days. Do you do that? I also can't remember what I do when I teach linear algebra. So anyway, we're not going to make any kind of distinction in how we write vectors. So whether it's something as a vector or a scalar, you just have to know from context. On the other hand, our vectors are always going to be lowercase, and our matrices and our linear transformations are always going to be uppercase. So you can tell the difference between a matrix and a vector, but not between a vector and a scalar without context. Okay, so here's a proposition. If A is an m by n matrix, then the mapping, we're going to call it L sub A, which goes from Rn to Rm, defined by what we just did. Is linear. Okay, how do we prove that?
Get two vectors and a scalar and just do it.
Yeah. Now our the way we set up the multiplication just above this is a nicer way to do it than if we did the general matrix multiplication with the double subscript. So that'll make our lives a little bit easier. But okay, let's let x and y be vectors in Rn, and let's let C be a scalar. Then we have, okay, we have LA of Cx plus Y is, well, it's A times Cx plus Y. Now, if we assumed that matrix multiplication is, I mean, right, depending on the background knowledge we're assuming about matrix multiplication, you know, this, we could just write CAX plus AY. But let's go back to our definition up top, where we defined what this is, and let's see if we can do it that way. This is the sum from j equals 1 to n of the jth component of x and y, which is a scalar, times the jth column of A. Okay. Now we're talking about just scalars times vectors, and I claim that it's clear that that's going to be associative and commutative. And so I am going to just allow us to write this as CXJAJ plus YJAJ. And I'm going to group that way. And now we see that this is literally CLA of X plus LA of Y. Okay. So we satisfied the condition of being linear. Okay. Questions? No? Yeah, Roger says in the chat, shouldn't we be taking dot products of the rows and the columns? Well, you know, if you do it this way, you don't have to. There's two ways to think about this. Again, let's go back to our picture. I will copy it down here again. Let's do it in green. This is our matrix A. And again, this is M, this is N. By the way, we're always going to be mapping from RM to RN. No, sorry, from RN to RM. So this is never going to change. Okay. And this is N. So once again, let me just point out, we have an M by N times an N by 1, and we get an M by 1. Okay. Now, there is one way to do this where you think about this entry here as being the dot product of, let's call this the third entry. Then it would be the dot product of the third row of A with, what are we calling this guy? Let's call this guy X, with this vector X. Okay? But instead, we can actually say that if we look instead what we end up seeing okay, let's look at the contribution of some particular column. We'll call this the jth column of A to this product, okay? So this is the jth column. Where does it show up here? Well, for every row, pick a row I. For row I, it shows up as a contribution to row I of the product here. And the way it shows up, you think to the dot, to the dot product formulation, is it shows up as that times the corresponding entry of X shows up there, okay? And that's what this other way of looking at it is telling you, okay? Is that instead of writing it out as a dot product and having to do the double subscripting, we can instead say the product is this linear combination of the columns of A with the coefficients given by X. Okay? I promise you, if you write out the algebraic, you write out the matrix A, double subscripted, it all checks out. Okay? Or you can just keep track of what's contributing to each entry in the product. Is that okay? Just a different way to look at it.
I'm surprised that I don't remember ever seeing this kind of definition in linear algebra. I feel like this has been such like a useful way to look at it.
Yeah, well, I mean, I can see why.
It's good for computation. Because you have to add everything together. I guess the dot product has is more meaningful maybe.
Well, so I can see why you didn't see it in linear algebra, and that's that linear algebra literally has to give you the dot product and double subscript version of multiplication. There's no way for that class not to teach that. And then the question is, is there time to teach you a different way to multiply? I mean, it's not a different way. It's just a different, bookkeeping, right? Same stuff's happening.
Yeah, I just feel like it would have saved a lot of pain of double subscripting in long proofs.
Yeah, perhaps. Well, you'll get to see. We're gonna do some of the same proofs here, so you'll get to see how much pain it would save. Okay, what did we do? Oh, yeah, okay. So this is left multiplication by the matrix A. That is linear. So given any matrix, we can get a linear transformation, which is the left multiplication by that matrix linear transformation, okay? This is all stuff you saw in linear algebra, I hope. I hope the course hasn't changed that much, that this isn't in it. Okay. Next proposition goes the other way. Yes, Keshav has a good point. I mean, this way of viewing matrix multiplication as a linear combination of the columns is good for a lot of stuff. I would argue it's good for everything. Let's start. We want to go conversely. Before we said that a matrix gives us a linear transformation. Now a linear transformation gives us a matrix. So let's do Rn to Rm. Okay. And we would like to claim that there is a unique m by n matrix A such that our transformation is the left multiplication by A linear transformation. Okay. Does this ring bells? Any?
Yeah, this is familiar.
Good. So, I mean, you combine these two results and you say, okay, for any matrix, it defines a linear transformation. For any linear transformation, there is a matrix. So they're the same thing, okay? Left multiplication by matrices is exactly the same as linear transformations. I went back and looked at the book that I always taught linear algebra out of, and I don't think it's changed since then. And frequently, we write this matrix A has a special notation. It's this square bracket of T. Okay. And in linear algebra, you make a big deal out of which bases you're using for your domain and range. So you would do actually square bracket T, and then you would denote the basis for the domain and the basis for the range. Okay? In this class, we are not going to make a big deal out of bases because we're just going to use the standard basis basically all the time. Okay, so we will never have to denote bases like that. And we're not going to have to talk about this matrix enough to really give it this notation. So we're not going to do this. So let me just say, but not here, just because we won't need it. Okay. So instead, we want to think about it this way. The transformation is equal to left multiplication by the matrix A. So there is a unique matrix A that makes this work. We good? Now, what was our comment that I wanted to take? You go back and you look right there at that comment. It says if you've got a matrix A, then the left multiplication A times the standard basis vector EJ will be the jth column of A. Okay. Well, we can just we can use this now to define our matrix A. So we go down into our proof here. So define A to be, well, I'm going to give you the columns, okay? Well, okay, fine. We'll do it this way. We're going to have how many columns? N columns. And we are going to define AJ to be, okay, we want A to match the transformation T, so we're going to define it to be the image of EJ under T, which, because T maps from Rn to Rm, this is a vector in Rm. Okay, so at the very least, we got the size right. We've got n columns, and they're all vectors in Rn. Okay, and now we just check. that we really do have it. So we want to check that T equals LA. Well, take some x in Rn. Okay, now in order to get it, in order to do this, what we really want to do is, I think we want to express it in terms of the standard basis. So then x is literally the sum of its coordinates times the standard basis vectors. Right? Every vector is a linear combination of the standard basis vectors, and that is what we denote their coordinates by. It's the meaning of the coordinates, basically. So now let's see. If we have t of x, if we take t of x, that would be the same. Well, I mean, we haven't changed x here. So this is this. Now, by linearity, so this is linearity of t. This is the same as the xj. Those, remember, are scalars now. Times the sum j equals 1 to n of t of ej. Well, now we've defined t of ej to be aj. So I didn't even really want to move this outside, did I? Well, anyway. Oops, I'm sorry. Okay, I definitely didn't want to move the xj's outside. It doesn't make any sense to have them outside. I'm really sorry. They can't go outside. Okay, let me turn on the lights for our last minute. Okay, and what do we have here? That's the product of A with X. Oh, Benjamin caught my mistake in the chat. Thank you, Benjamin. I didn't see it in time to, well, I mean, I caught it myself before I saw that. Okay, I mean, that's it. And we're trying to prove an equality. We just proved the equality. Okay, because actually everything just was an equality here. Okay. Now, one thing I'm not going to prove, I'll do this in the lecture notes. So this is another proposition. We aren't going to get to it, but I do want to state it. So let's say you have S from Rn to Rm, and T from Rm to R. And we kind of run out of good variables at this point. Definitely can't use O, so we're going to skip O and go to P, I guess. Okay. Then what could we do? We could do S first and then T. This would be a map from Rn to Rp. Okay. And T of S, oops. And if let's see, S is LA and T is LB, then this composition, oops, would be, well, by definition, it would be LA followed by LB. Because I haven't changed anything. But then the whole point is that it's L of BA. Okay, so I don't understand your comment, Benjamin. Yes, I should have said it's linear, I guess. Because of the and. Yes, now I understand. Okay, yes, the composition is still linear. We should say that. And the point is, if the matrix for S is A and the matrix for T is B, then the matrix for the composition is the product matrix. Okay? So there you go. I mean, that's the one lecture version of why matrices are important. And the way they're going to fit into this course is we want to take derivatives. And what are derivatives of multivariable functions? They are essentially linear transformations that approximate the function at a point. Okay, just like your tangent line on the, if you're just in the plane, your tangent line is representing your derivative. Here we're going to have some linear transformation representing your derivative. Okay, so I believe, so enjoy your recharge day on Wednesday. When we come back on Friday, we're going to be looking at, I think we're going to look at the metric we're using on this space in a little bit more detail. Okay, so I will see you then.